way, but a very direct way. My belief is everything we're about to talk about, you should have been able to do by the end of an AP Physics 1 class. So those of you who, who didn't have physics before, I understand how challenging that could be. But for those of you who did, I'm counting on you guys to not have to be, hear this 1,000 times just once. So let's get started. And I'll grab those lights. All right. You don't like the pumpkins?
No, I just thought it was like, he thought they were alien eggs or something. You know, it's just something
Okay. Alex thinks they're alien eggs. I think they're pumpkins. You guys at home, what do you see?
I'm seeing the alien eggs.
All right. Alien eggs. That's what it is. So now you know what my next background's going to be, right? So. Good one. That was good. That was smart. Why is Joey sitting in the dark?
The window, like the light is just coming through and hitting the camera. So like it won't focus on my face. So like if I move in front of the window, it sort of helps.
I gotcha. You just like sitting in the dark. You can be honest.
Yes,
okay.
Very spooky. Not spookier than alien eggs.
That's right. It's not spookier than alien eggs. All right, here we go. So we're going to take a look at, this is all, in my opinion, these are all just very basic. They're all very straightforward. We did two basic-ish ones on Tuesday with the car going over the top of the curve and car going under the top of the, over the top of the hump and under the dip. So we did those two examples in class, right? We drew it, but we didn't like work them out. All right, well, we should work those out first. So let's take a look at that. These are all centripetal acceleration problems. So these two examples of the roadway. Ooh, that's not very circular. Let's try again. These two examples of the roadway problem. Boy, that's just as terrible, isn't it? My word. I'm just not. Maybe I just need to take a little more time and care when I draw, and that would make it better. That's where it's staying because I'm just not going to do it again. Let's take a look at this, the dip in the road, a wash. So anybody, I think I should have said something about, if you live someplace like I did where there actually are washouts in the road, basically they just don't build bridges here. They just let the water flow right through it. So if it's that day where it's going to be rainy, that 3 days out of the year in Arizona, you just don't cross the road that day. You wait an hour for the water to subside and then you go across. They'd have these kind of things there. So a problem like this is more, there's no chance that you won't be able to make it into the dip. So you tend to ask questions like, what would be the normal force on the car when it's at the bottom of the dip? And these are pretty straightforward. You give the car a velocity, and you recognize that as the car makes its way into the dip, it's at the bottom where we deal with these forces. Now, in AP Physics 1, we'd focus just on the bottom. Because at the bottom, we know there's going to be only two forces of importance here. An upwards normal force, which must be greater than the weight. And it has to be like that because there's got to be an unbalanced force in order to travel in any circular path. So in this instance, the net force is going to be equal to MA. And I'll put the C here to remind me that this is due to the fact that it's in circular motion. Now, there could be other forces. The car could be hitting the brakes or even speeding up. All of that's fine, but we're focusing on what is happening to the car from the ground at the moment it's at the bottom. And again, this would be a fairly straightforward AP Physics 1 style question. We'd recognize first that I'm going to make the upwards direction positive because that's got to be the direction of the acceleration. Something that I would really encourage you put into your notes, that for centripetal motion problems, it is much easier on you if you make the acceleration direction the positive direction for your forces. This is one of those cases where I wouldn't be too arbitrary about it. I'd work diligently to make that the positive X or the positive Y direction. But also that's going to mean that we'll have two forces. And it's at this time where it's probably appropriate that we replace our expression for acceleration with the centripetal acceleration, giving us an opportunity to solve for the normal force. Now, really what I want to point out here is we get this portion of the normal force that has a constant component and a speed variable component. One of the first times you'll be given a question like this, you'll be asked something like, how fast do you have to be going to feel 3 times your weight? And a lot of students get thrown with that kind of wording. But if I ask you that question, what I'm really saying to you is that the normal force on you is going to be 3 times your weight. It doesn't matter that it's the weight of the car or the weight of you. Because if I ask how fast you have to be going to experience 3 times your weight, you're going to put in 3 mg for the normal force. And it's not going to matter whether we're talking about the car or talking about you. There is a single velocity that's going to make that happen. Cancel out those m's. Move the 1g over. And it gives you a clear pathway to figure out how fast you have to be traveling in order for you to feel 3 times your weight at the bottom of that dip. Those are pretty straightforward, and I don't feel there's a whole lot here. Of course, the questions that tend to throw students aren't ones at the bottom. In AP Physics C now, there's no reason why we couldn't consider what you're experiencing over here. And in these questions, you are still on the circular path, but now with the weight downwards and the normal force at an angle, the net force in the system not only isn't 0, but it could be acting in more than one dimension. You might think that it might be best to line this up with the weight, but you really do want to line it up still with the direction of the centripetal acceleration, which means using a coordinate system that's lined up, like this, and knowing that you're probably going to have 2 accelerations. One from the hillside, and then one that is that's radial. I know I've always told you to try and make these problems be so that there's only one acceleration. That might not be suitable any longer, because only the one that's pointing towards the center of motion is the one that's causing a centripetal acceleration, and that's the one that has to be proportional to v squared over r. You can have an acceleration in another direction. That's changing your speed. So in this situation, if we let off the gas right there at the bottom and coasted, then our normal force and our actual tangential velocity are both going to be changing due to the way in which the car is being acted on by the normal force and the weight, let alone if there's friction or anything else acting in the problem. Now, the other kind of style of question that's in this same genre is when you're having to go over a hill. It's a similar kind of problem, but generally in this problem, we're not going to ask, you know, what's the normal force on the vehicle? We're going to probably ask a question that's more based on what's happening here, something that's going to maybe question the student and have them recognize there might be limits. Generally, the question here is, what's the maximum speed the car can safely manage traveling over the top of the hill? That's generally in line with the idea that when we make it to the top here, we need an unbalanced force downwards. Weight of the car doesn't change, which means that as we go faster, there's probably going to be less and less normal force. A lot of students really struggle with this, but keep in mind, your car has inertia, as do you. You want to travel in this straight line. That's the goal here, right? Inertia wants to travel in a straight line unless acted on by some outside force. Goal's the wrong word. It's just nature. Now, you won't travel in that straight line because you're being acted on by gravity. But if you want to travel in a circle, you don't want to be just acted on by gravity. Because if you are just acted on by gravity, your path becomes that of a projectile. In order for you to trace the circle, you have to travel in such a way that the combination of forces allows for a net force towards the center that's still proportional to v squared over r. So if you go too fast, you start having difficulty. In this problem, our threshold has to do with how fast we're going. Meaning, I've got two forces acting. I've got gravity and I've got normal. Please notice how I've switched to make downwards positive. These have to be equal to mv squared over r. I stay on the roadway as long as there's a normal force. But the moment the normal force goes to zero, I'm no longer in contact with the road. So I want to make sure that I stay in contact with the road. So what is that breaking point? What is too fast? Well, that's when the normal force goes to zero. So that gives me a clear path to figure out. There it is. That's my speed limit. If I go slower than that, there'll be a normal force. If I go faster than that, or if I go at that speed, the normal force is zero. But again, that calculating at the top of the hill, that's AP Physics 1. And of course, there are students in AP Physics 1 that struggle with this a lot. But I need you not only to struggle with it, but I need you to recognize that there's the potential for you to leave the road here. And leaving the road here is different. A, you're a projectile with a launch angle now, where you can launch yourself over the hill. But second, the normal force is acting definitely along a radius, but the weight isn't, making this a much more difficult problem. How do you line it up? How do you decide what the best way to line this problem will be? Still telling you the best way to line up this problem will be with the angle of the curve. And make your positive direction towards the center of the circle. Now those are some of the basics. But we don't have to have hills and thresholds to make our problem tough. We can make our problem, just as tough by talking about just making a nice, quick left turn. Oof. Let's do that again. Let's say we're rounding a turn and our car is traveling at velocity v. Let's say the turn has a radius of r. And let's say there's a coefficient of static friction of mu s between the car and the road. What's the maximum safe speed of the vehicle? Car has a mass of m. The maximum safe speed of the vehicle, and still navigate this turn. I'm not going to do this problem. I'm going to have you guys do this problem because I think you guys can. So I'm going to hit the old pause button here. Where should I begin this problem? To you.
Okay. So there's two directions with the forces. So you go off your body diagram.
Okay, let's start with that free body diagram. What do I got?
You have the weight going downwards. That's the normal force going upwards. And then friction to the right.
Like that?
Yeah.
Okay. How many of you agree with this? You got some people backing you up. What direction do we want the car to turn? So we need the unbalanced force to be in the direction of the turn. So let's make that change first. All right. So Alex got us off to the right start. So now we have a good free body diagram that we can use. So, where's my seating chart? That way I can be more random. What? No, I'm going to pick on lots of folks. Once I picked you, everybody else is kind of relaxed, and I really don't want that. So, Jaden, where do I go next?
I'm not quite sure why, but I just kind of said friction equal to mg squared above over r, and then simplify that to u mg equals mg squared over r.
Okay, I couldn't hear some of that. Can you repeat yourself a little louder? Yeah.
I said friction equal to mg squared over r, and then simplified friction into u mg equals mg squared over r.
Okay. I'm going to back you up just a little bit, not because I don't think you're doing anything wrong, but because I'm trying to make sure I've explained this in a way that other people can understand it too. You said you set friction equal to mv squared over r. What that means beforehand is you've decided that this is a Newton's second law problem, that there's an unbalanced force. Now, I'm not saying this to correct you. I'm saying this to make sure that the people who have never had physics before understand where we got this from. And then I assume, because you skipped many steps here, that you broke this up into an x direction and a y direction. Is that true? All right, so what direction did you make the x direction? All right, so net force in the x direction. Is this the one that's balanced or unbalanced? All right. So your net force in the y direction you set equal to 0. All right. So where'd you go after this?
I'm not really sure. I'm kind of stuck a little bit.
Okay. So this is an unbalanced force acting on our system. The thing that we have to remember about this is that the object's speed isn't changing. This is the fact that it's making a turn. So I like to make sure that we emphasize the fact that this is a centripetal acceleration, which means our net force in the x direction is equal to mv squared over r, in order to emphasize the idea that our object is making a change in direction. And its direction in a circular way. So our unbalanced force equals mv squared over r. We are simply replacing a with v squared over r. And we're still doing the same thing we did before. We are adding up all the forces in the x direction. But there's only one force in the x direction, and that's friction. So this is where that force equals mv squared over r came from. I had some concerns, which is why I wanted to make sure we drilled it down, okay? So, Ryan, where do I go next? I don't think we can say equal to. No, we can do that. Sure. So we can state that the frictional force is going to be less than or equal to mu times the normal force, which if that's the case, this is going to be the substitution point, right? We're going to substitute into this formula. So we can make one substitution, right? Because we know friction is mv squared over r. But Sana, what am I going to do next to deal with that normal force?
I know that you have to, so in the y direction, you would have n equals mg. Which direction is positive and negative for this one?
For the y direction?
Yes.
Yeah, I don't care. You pick.
Okay. For the n would be positive, so would it be n equals mg?
Yeah, it's going to be the same either way.
Okay.
If you made downwards positive, you would just get mg equals n. So that's fine. So now we can do this substitution too into the friction equation, which is going to give us mv squared over r is less than or equal to mu times mg. Now I'm going to assume most of you guys who did, had a solid job last year, you got this far. Maybe not with the inequality, maybe you kind of turned into inequality. But is there any problem getting to here? I want you to keep those inequalities here because this is where we separate us out and make sure we understand threshold values. Canceling the m's there and solving for v, we're going to get v squared has to be, solving for v, because this v's got to be less than or equal to the square root of mu s g r. First thing I would do for something like this, because there's so many substitutions, is check the units. G is going to be in meters per second squared. R is going to be in meters. That gives us meters squared per second squared. Square root of that is meters per second. So that tells me the algebra was done right. I didn't make an algebra mistake. Doesn't tell me if I have the right answer or not, but it definitely helps make sure that I have good algebra. I'll point out all the things that are here that we probably know. For example, mass of the car didn't matter. Now, that might surprise you. Mass of the car is what determines the normal force, but because mass is also inertia, those two parts of the equation seem to go away. Now, in real physics, the mass of the car would have mattered. And we know this. But that's not because of anything we've done wrong here. We're taking too narrow a view. We're assuming all the forces act at the center of mass of the car, but they don't. These forces act in different places on the car, and that can have striking differences on where the mass is located. And therefore, the mass would matter in real life. Why a loaded truck probably has to go slower in a turn than an empty truck. Where that center is located, where that mass is located, makes a difference. Now, the things that obviously do matter, how sticky the tires are. They're less sticky, that's going to lower. I see a direct relationship there. You should ask yourself these questions too. If I want to go faster, having a bigger radius would do that. It shouldn't be too big a surprise, though, that G shows up here, because that's what's holding the car on the ground. So on a place where there's more G, yeah, you can go a little faster. We don't really get a chance to adjust that very much, though. Good example. You guys feeling okay? Take it up a level.
Mr. Shelton?
Yeah.
In what situation do you flip the inequality sign?
Well, I can think of only one reason why you'd flip the inequality sign, and that's because you multiplied both sides by a negative value.
That's the only situation?
That's the only mathematical reason to flip an inequality sign. Now, I'm saying that knowing that I could write this I have technically flipped the inequality sign, but I've not changed the meaning of this at all. So if I solved for V and left it on the right side of the equation, my inequality would be flipped, but the statement is still the same. Even though we say it left to right, greater than or less than. For us, remember, it's a comparison. And we're trying to say that, okay, look, our velocity has to be under this value or else we're going to have problems. Is that good? All right. All right, we're going to take it up a notch. And not much. This is where your lab's going to be. And it's one of my favorite labs because people can hit themselves in the head with this lab. And we're going to do this lab, and we're going to have people at home do this lab because they can find most of the materials around their house to do this lab. You're going to take a hollowed out pen tube, you know, like from a Bic pen, and you're going to put a string in it, and you're going to hang a weight on one end of the string, and the hollowed out tube you're going to use as a handle so that you can have the string pass through it, and you can connect a smaller mass to it, and then spin it above your head. Can you imagine what this looks like? I can imagine what it's going to look like. And I think I've kind of picked out who I think is going to be able to handle this and who's going to get hit in the head. There is the potential for you to choose a Bic pen that is a little too old and it can cut your string. So we want to use a new Bic pen. And if you're in class, I actually have these ones that are made out of glass, and so they're nice and smooth. But like I said, I don't have too many of those. And even in this room, there's more lab groups than I have glass tubes. So some of you are going to be getting the Bic pen, and that can make for some funny times. We're going to call this little m. We're going to call this big M. And we're going to spin this so that if I look top down on it, the mass is going to go kind of in a circle like that. Now, because it takes an unbalanced force of tension for this to happen, we have the tension being created by this mass we hung. Technically, this is a two-body problem. But our goal is going to be to keep the mass suspended. So it's not a dynamic problem. So I think we can all agree then that the tension in the cable is going to have to be equal to whatever mass we hang. So yeah, technically two-body problem, but not really. Now, here's what I want from you. I would like you to tell me, in the case of this problem, the balance point here. Meaning there's going to be a point of balance where your spin speed and this radius and all that has to be balanced so that this mass doesn't move. Where we spin it fast enough where the inertia of the mass going in the circle balances the tension going down the center. But be careful, because in this problem, the truth is the weight doesn't stay perfectly sideways. No matter what you do, the weight tends to make an angle like this. And you should know why, because we've talked about it. There has to be an upward component of the tension to balance the weight of the object. So therefore, this cable must make an angle theta with the horizon. So I would like an expression for the velocity of the object in terms of mg, little m, L, and theta. Does everybody understand what I am asking you to find? All righty. I will give you a moment. I don't think you need help from friends. This is hardly any different than what we just did. Take a few minutes, start with net force, and see if you can work this out. All right. Let's record it so we have it for all posterity. All right, Luke, how did you do it?
So the first two body diagrams I did was from the lower mass, where tension is up, energy is down, and looking forward.
Okay, a little unnecessary only because I told you this from the beginning. So, but I'll accept it. That way you can sound like you know what you're doing.
The second free body diagram has energy down and then tension at an angle theta relative to the x-axis. The tension is to the left.
Like so.
Like so.
Excellent. Keep going.
So I figured that they have to be the same tension. Two tensions have to be each other,
Great.
or the bigger knots to be held up. So net force in the x direction of the top divided by length has to equal m.
Okay, so let me stop you. So you're going to put your horizontal direction like that, and you're going to say net force in the x direction equals ma. All of that sounds good. Yes, we want the stopper to stay at the same height. So I assume that you're going to go another step and tell me about the net force in the y direction. I'm waiting.
So net force in the y direction equals 0.
Okay, great. You're doing fantastic. This is theta right here, right? Oh, good, good, good. Keep going.
So t sine theta has to equal mg.
All right, let's. I'm gonna write that down. So the first thing he did was he added up all the forces in the y direction, which gave him t sine theta minus mg equals 0, or t sine theta equals mg, little mg this time. Great. Let's keep going. You're doing fantastic.
So from there, I figured the x direction, m v squared over r has to be equal to t cosine theta.
Okay, in the x direction, you changed a to be v squared over r. Fantastic.
And then set that equal to t cosine theta.
Great. You're doing awesome.
Because like you set me up.
Maybe you got it right.
Since the tensions have to be equal to each other, the tension equals big mg.
Okay, so you're replacing big mg with tension. Good, good, good. Now what?
Originally I divided by m and multiplied by r both sides.
Okay. I don't think anything's wrong here except that you can't have you can't have r in your answer.
Yeah, I figured that. You said it. You want it in terms of L?
I would like it in terms of L.
In terms of L?
Does are R and L equal?
No.
That's the first thing I want to point out, because I think a lot of you replaced R with L. And if you did, that's not true. R has to be the perpendicular distance from the axis of rotation to your object. Let me say that again, because I've not covered that, and this would not have been covered in AP Physics 1. But your radius of curvature is the perpendicular distance from your object to the axis of rotation. The axis of rotation isn't a point, it's a line. It's a line that is perpendicular to the plane of your circle. Now, you don't need to know all of that, but you do have to understand that R isn't necessarily the length of the string here. That's where a lot of people make a mistake. So you need to find a way of expressing the length of the string. I'm sorry, you have to find a way of representing R in terms of the length of the string. And based on the triangle I got going on there, it's not hard. It's just L cosine theta. Do you see it? So M over M times L cosine theta times G cosine theta equals V squared. Now we got it. I had a feeling Luke was onto something, but just had to make sure. Now you can solve this, right? You can get an expression now for velocity. And it tells you lots of stuff. So when I do that, I want to get to the end here just to point out a couple things. So capital M, L, G, cosine squared theta all over little m. There's a lot going on here, but the m's, their units cancel out. On the numerator, I have L, which is in meters, G, which is meters per second squared, and cosine squared, which has no units. So my units inside the radical, meter squared per second squared. So I have a high level of confidence that our algebra is done correctly. And look, this tells me things like if the mass that I'm swinging is bigger, I can spin it slower. But don't think that that's the end of the story, because some of you are smart, been drinking milk, and you can point out something else here, something that we may not have talked about. The fact that mg sine theta, not mg sine theta, that mg equals t sine theta, which in this problem is mg equals capital MG sine theta. Do you guys see where I'm getting this from? This is the y direction, right here. Which tells me that there's something about the angle that's related to the masses I use. First, it tells me that the angle can never be 0 unless the mass I swing in a circle has no mass, or the mass I hang is infinitely massive. So there's no way to get a theta of 0, none. But it tells me that if I make the mass that I'm swinging bigger, the angle's going to get bigger. And if the angle gets bigger there, that means the angle gets bigger here, meaning I got to swing at a smaller velocity. They're all interconnected here. Okay, we did a bunch of, I'd say, escalating level of difficulty, but not terribly difficult. So tomorrow, my expectation is we can maybe start a lab, but more importantly, look at some mechanics levels.